Here's the relationship between a sequence and a series. A sequence, this is in fact is the sequence of odd numbers 1, 3, 5, all the way up to 2n minus 1. A series is the sum of the terms of a sequence. Now, most of the series that we are going to work with will just be a finite sum of some sequence terms. But in any case, when I take a sequence and I add the terms together, what I get is called a series. Now, in this case, I'm adding the first 4 odd numbers in this series. I have this notation that stands for that. This is a capital sigma, the Greek letter sigma, in Greek it's the letter S for sum. And it starts at I equals 1 and goes up to 4, and you want to add all the terms that look like 2i minus 1, starting with I equal 1, going up to and including I equal 4, and catching every integer between this one and this one. So it's I equal 1, I equal 2, I equal 3, I equal 4 into this expression right here, and I add each of the terms together that I get. So this notation right here is shorthand notation for this sum, 1 plus 3 plus 5 plus 7. So this is sigma notation or summation notation, and it's used to represent a series. So let's go to the board now and look at our first example. It says expand and simplify. And all we want to do here is get used to this notation, this summation notation. So what this notation right here means is to take all the things that look like this, starting with I equal 1, going to I equal 2, I equal 3, and I equal 4, and adding each of these things. So what it looks like then is this. 2 times 1 plus 4 plus 2 times 2 plus 4 plus 2 times 3 plus 4 plus 2 times 4 plus 4. So I use all the integers in order, starting with 1 and ending at 4. So here's I equal 1, 2, 3, 4 in this formula right here, 2i plus 4. Now I can just simplify this. This is going to be 2 plus 4 or 6. This will be 4 plus 4 or 8. This will be 6 plus 4, which is 10. And this is 8 plus 4, which is 12. Now when I add all of these together, 6 plus 8 is 14, plus 10 is 24, plus 12 is 36. So this really is just a fancy way to write the number 36. So again, what this notation means is to take all the things that look like this and add them up, starting with I equals 1, going up to I equal 4, and including all the integer values of I between 1 and 4. Let's look at another example. I have the sum from I equal 3 up to 6 of negative 2 to the I. So this stands for negative 2 to the third. See, it's a little bit different than sequences in that we don't always start at 1. Sometimes we can start at 3 or 4 or 5, whatever we want. Negative 2 to the 3 plus negative 2 to the 4 plus negative 2 to the 5 plus negative 2 to the 6. I just used the formula exactly the way it's given, replacing I with 3, 4, 5, and then 6, and then adding those terms together. So what do we have? Negative 2 to the third is negative 8. Negative 2 to the fourth is going to be 16. Negative 2 to the fifth, 32. And negative 2 to the sixth, whoops, take that back. Negative 2 to the fifth is negative 32. Going a little fast here for me. Negative 2 to the sixth is positive 64. So if I add the negative numbers together, I have negative 40. Plus, I'll add the positive numbers together. 16 plus 64 is 80. And those come out to be 40. So this sum from I equal 3 up to 6 of negative 2 to the I comes out to be 40 when I expand it and then simplify it by adding each of the terms together. Now, it's not sometimes the term in the summation notation itself will contain another variable besides I, and in that case you may end up with some things that can't be simplified, so all you can do is expand them. Let's look at our next example. We want the sum from I equal 3 up to 8 of x plus I to the I. So I is the index of summation here, that's what it's called, and it's the variable that varies with each term right here. This x has nothing to do with this I, so we're just going to leave it alone. It's part of this term. So I get x plus 3 to the third power. Then I get x plus 4 to the fourth power, plus x plus 5 to the 5th power plus x plus 6 to the 6th power plus x plus 7 to the 7th power plus x plus 8 to the 8th power, and that's when I stop because I want my summation to go from I equal 3 up to and including 8. So it's 3, 4, 5, 6, 7, 8. And notice that the only thing that changed in the formula each time was the i's. So that x stayed the same in each case. Now, this would be a pretty difficult problem to do, x plus 8 to the 8th power, to multiply all that out. We'll actually see how to handle expressions like this later on in the chapter using the binomial expansion. But for right now, we would have to leave this in this form right here. We can't simplify it any further. What I want to do next is look at some sums and see if we can't find a general term for them and contract them back to summation notation to one expression using that summation notation. So let's take a look at the next example. It says, write with summation notation, I have 3/4 plus 4/5 plus 5/6 plus 6/7 plus 7/8. Now, I don't want to actually add these together. All I want to do is write this as an expression using summation notation. So let's see, this is 3 over 3 plus 1. This is 4 over 4 plus 1. I'm trying to see a pattern here. 5 over 5 plus 1. That is, the denominator is 1 more than the numerator. 6 over 6 plus 1, and 7 over 7 plus 1. So if I look at the 3 as the 4, 5, 6, and 7 as the things that are changing, and the 1 is staying the same, all of these have the form of I over I plus 1. That is, the denominator is 1 bigger than the numerator. And I want to add them all up, starting with I equal, that's right, 3, and going up to I equal, correct, 7. So this looks like the sum from I equal 3 up to 7 of all things of the form I over I plus 1. So when I put in 3, I get 3 over 3 plus 1, that's 3/4. Then I go to the next number, 4, I put it in, 4 over 4 plus 1, that's going to be 4/5. 5 over 5 plus 1, 5/6, so on and so forth. So it's the sum from I equal 3 up to 7 of I over I plus 1. So I didn't want to do this addition right here. All I want to do is contract it down and use summation notation to write an equivalent statement. Okay, let's look at the next example. Example 5, 4 plus 8 plus 16 plus 32 plus 64. Well, these again look like powers of 2, 2 to the 2nd, plus 2 to the 3rd, plus 2 to the 4th, plus 2 to the 5th, plus 2 to the 6th. So they all have the form 2 to the I, and I want to add all of them together, starting with I equal 2. That's right, I equal 2, and ending at I equal 6. So this is the notation that I would use to write this sum in a compact form using summation notation. So again, I know that you know how to add these numbers up. That's not the point of this problem. The point of this problem is to take a sum that involves some formula that's being repeated and write it using summation notation. So each of these things that we've worked with in this section right now have been called series.